Good morning. It's my honor to present my work in your conference. I'm Daegyu, PhD candidate in DYROS lab of Seoul National University. I will present my work titled Online Telemanipulation Framework on Humanoid for both manipulation and imitation. The teleoperation robot is very promising technology because it can transfer human skills to the robot. So the robot can do hard and dangerous work instead of human leveraging the operator's intelligence. Also, the teleoperated robot can be used as a physical communication tool as demonstrated in this video. But there are many problems to develop a teleoperation system. Among many problems, I focused on motion retargeting and control problem in this work. Human and humanoids are different kinematically and dynamically. Therefore, an appropriate motion retargeting algorithm should be implemented for the intuitive humanoid teleoperation. There are several previous works related to motion retargeting. Those can be divided into two fields, computer graphics and robotics. In computer graphics, they usually use deep learning methods to train the retargeting network. Those data-driven methods showed high-quality results in the visual similarity. But the deep learning-based motion retargeting is not suitable for real-time teleoperation because the network should be trained for each operator. Also, such nonlinear mapping causes large adaptation time for the human operator. On the other hand, in robotics field, majority of works use a kind of linear mapping algorithm in operational space or joint space. The linear mapping is intuitive and easy to adjust for the operator, and computation load is light. However, in robotics, many studies do not consider the visual similarity, but only focus on performing the remote task. So, we propose a real-time teleoperation framework, including linear hand position mapping method based on calibration poses and orientation mapping method. Using the proposed method, both visual similarity and transferring the intentional behavior are improved. This diagram shows the proposed teleoperation framework, and there are two main blocks. The first block is motion mapping, which transforms the motion of the operator to the desired motion of the robot. And the second block is the inverse kinematics using hierarchical quadratic programming. In this presentation, the motion mapping will be more focused. This shows the proposed motion mapping method and its components. The motion mapping method consists of hand position mapping and orientation mapping. And the orientation mapping is divided into absolute orientation mapping and relative orientation mapping. There are three design goals for the motion mapping algorithm and corresponding three design decisions. The first goal is to make an intuitive telemanipulation system so that the operator can adjust to the system quickly. For this purpose, the linear hand position mapping and the absolute orientation mapping are used. The second design goal is the appearance similarity. The calibration-based hand position mapping and the absolute orientation mapping contribute to this. Lastly, it is desired to design the teleoperation system without complex preparation procedure. To achieve this goal, the relative orientation mapping is used. Also, for the fast calibration time, only three poses are recorded. Calibration procedure is introduced to specify the model for each person. In this model, the shoulder position and the arm length should be determined. For the calibration, 3 calibration poses are recorded: still pose, T-pose, and forward pose. Using 3 calibration poses, the shoulder position and the arm length can be calculated based on 2 rules below. First, the shoulder should be located in the identical distance from 3 calibration hand positions. Second, 3 calibration-based vectors should be as orthogonal as possible. For the hand position mapping, 3 calibration vectors are used as a basis of coordinate system. Then, the current hand position of the operator can be expressed as a linear combination of the 3 calibration vectors, as shown in equation 1. The optimal mapping vector can be calculated under several constraints using quadratic programming. After that, the optimal mapping vector is transferred to the corresponding calibration poses of the robot. Finally, the desired hand position of the robot can be obtained, as shown in equation 2. Next, I will introduce the orientation mapping. The absolute orientation mapping uses the operator's orientation itself as a desired orientation of the robot. And head and hands belong to the absolute orientation mapping. On the other hand, the relative orientation mapping measures the changes of the orientation of the operator and rotates the corresponding robot's link from the initial orientation. The relative orientation mapping is used for upper arm, shoulder, and upper body. There are pros and cons for each orientation mapping. The absolute orientation mapping has pros in that it does not require an initialized pose. But for the absolute orientation mapping, the tracker should be attached to the specific pose regardless of the person. However, the relative orientation mapping has the advantage in that it relaxes the constraint on the tracker position. This makes the preparation procedure easier, but predefined initial pose is required to use the relative orientation mapping. After mapping all the motions of the operator, the desired motion of the robot should be controlled. However, there are multiple tasks and constraints more than the robot's degree of freedom. So, HQP is used to impose hierarchies on the tasks. The tasks for each hierarchy are summarized in the table. And for the details, please refer to the paper. This is the result video comparing motion similarity between different linear hand position mapping algorithms in simulation. The one-to-one mapping uses the operator's hand position directly as the desired hand position. The proportional mapping scales the operator's hand motion according to the ratio of the arm lengths between the robot and the operator. And the proposed method is shown at the lower right corner. As you can see, the proposed method looks more similar with the operator than the two other methods. In particular, when the operator extends his arms to both sides, the proposed method best imitates the operator. In the second experiment, a hypothesis is made upon a lot of experiences testing the proposed method. First, human has a distorted sense of space. Second, 3 calibration poses can capture such distorted sense of space approximately. Third, the proposed method can extract the intention of the operator in the mapping variable and can retarget the intended motion more correctly because the proposed mapping method uses calibration vectors as the basis of coordinate system. To test the hypothesis, user study was performed. Experiment is conducted by a human subject, and subjects were asked to draw 10 perfect same circles with constant speed in front plane. The subjects conducted the experiment with their eyes closed. After obtaining the circle trajectory, the original circle and the retargeted circles are compared to determine which circles are closer to the perfect circle. The circle index is introduced to measure the similarity to the circle. It is calculated by the RMS error of the regression over the circle radius. The smaller the circle index, the closer the hand trajectory is to the perfect circle. Here is the result of 4 subjects. They draw the circles using each hand, and hand trajectory is retargeted using the proposed hand position mapping. And we found that there are more cases where the retargeted circle has smaller circle index than the circle index of the original circle, which means that the retargeted circle is more circle-like than the original circle. This result supports the hypothesis that the proposed mapping method can retarget the intended motion more correctly. I will conclude this presentation. Our contribution is that the teleoperation framework is proposed, which enables both performing remote tests and social interaction with high visual similarity. Our framework has pros and cons. Pros are that our method shows high visual similarity than the other linear mapping methods, and improves the performance of transferring intentional motion using calibration basis. Also, we make the preparation procedure easy by relaxing constraints on the tracker position. Cons is that our method needs calibration, so the performance of teleoperation can be affected by the quality of the pose calibration. That's all of my presentation. Thank you for listening.